All right, everybody, what is going on? This is Chandler. I thought that you guys could use a little bit of extra help, just kind of going through the orbits and sketching, just because may have not have been clicking in class, and our review may not have been helpful to everyone. So just want to cover it again. So I am coming from the homework 2, which the homework solutions are posted at Elms now if you didn't know. But yeah, so first we have this orbit here from problem 4, orbit C. Yeah, and I'm just gonna kind of walk everyone through on how to sketch these orbits. So let's go ahead and start. So right off the bat, we can go ahead and look at this eccentricity and immediately tell that's an ellipse, right? It's most common for drawing 2D orbits that it's going to be an ellipse. So usually when you are asked, it's an ellipse, but not always. Don't take my word that it's always. So let's go ahead and draw this 2D orbit, shall we? Oh, that looks like a hot dog. Let's go ahead and nice egg here. Yeah, we'll work with that. You guys don't get iPads on the exam, so I got to go with my bad sketches. So it's really easy. You take your eccentricity, it's an ellipse, so you go ahead and draw a kind of ellipse, right? Making sure that it's in a round and that your point is closer to one side than the other. One of the big things we are looking for too is that this periapsis point that I'm going to define here is the closest point to here, right? This is actually periapsis, right? We want to make sure that that's true. So yeah, the other thing you can do is just go ahead and draw a straight line right through. Yeah, so that was easy, right? We've already got a ellipse, we've got our periapsis labeled, we have our center labeled. What's next? Well, we want to go ahead and look at these other ones, right? So what do we actually need? Well, we needed the eccentricity. Okay, well, let's go ahead and take a look at this inclination, right? So a real quick 3D sketch, right? Not even drawing, but just the coordinate system. So we remember inclination is essentially the angle between the angular momentum vector and the positive y-axis, or z-axis, excuse me. So what does that actually mean? Well, that means if this is our h vector here, that this is our inclination angle. Okay, so let's clarify. Let's say that this is the negative y-axis. This is positive y. If the angular momentum vector is up above that, right, our inclination is going to be less than 90. Okay, well, we have an inclination that's greater than 90. So what does that mean? So that means that our h vector is going to be somewhere pointed down here. Something like that. We'll get into this 3D sketching orbits of where our h vector actually is, but it's somewhere down here in the negative z plane. So what does that mean logistically for you guys? All right, so really easy for me is when our inclination is greater than greater than 90, we want to be viewing from it from the up down, right? So whenever we are drawing sketches, I always draw them where we are looking from the top down. Okay, so what does that actually mean? That means that our h vector is going to be into this page, right? The cross means down, the open circle means up, right? So if I just circled the central body, then it would means that the h vector is coming up, which we are viewing from in the top down usually. That is, again, my method. Not necessarily the correct way or the best way. It's just my method of how I do things. And I'll go over a little bit later on how to draw the orbit the other way. But for now, let's just stick with this. So we've defined our inclination as this, right? So that'll help us define where our h vector is. So let's move on. Do we need cap omega at all doing 2D sketches? The answer is no. We're going to move on. Let's look at our small omega. So our small omega is where we are defining our ascending node to periapsis. All right. So the best way to look at that actually is we have our periapsis here. And since we are defining the spacecraft going in this direction, and so because of these assumptions, right, we are assuming periapsis is here. We are assuming that the spacecraft is going in a clockwise direction, and then we are now defining, as our h vector is down, we can define our omega, our negative omega, in this direction. Now again, I say all of this, and we'll cover it later when I redo this sketch, because it's backwards otherwise. And we want to make sure we're using our omega in the correct direction. So we take off 30 degrees. So we're going to move this over a little bit, because I like to draw it nice and big. Small omega is about 30 degrees. It is 30 degrees from this point along our orbit sketch. All right. And so it's about that line. This is the descending node. This is the ascending node. Now, a couple things on this, right? Why are we given positive small omega if we're just going to use the negative omega? Okay, well, small omega is defined as the angle between our ascending node to our periapsis. So if I really wanted, all I would have to do is just define this as omega, which is true. But we are kind of going backwards here, right? So it's negative omega, and that's okay. Another thing, right? This is the ascending node, right? It's periapsis to ascending node, right? So to label these backwards would be wrong. That is something to take note of on the exam. All right, well, we got our ascending node, we got our descending node, we've got our periapsis, angular momentum. What's left? Well, we have our spacecraft, right? True anomaly is defined of where our spacecraft is from periapsis to somewhere else along the trajectory, right? So we have defined this trajectory as going clockwise, all right? That means we take periapsis, we go 180 degrees around, and it just so happens to be an apoapsis, that this is our spacecraft, all right? Now, the last thing that I didn't write down, but you could easily tell, right? Look at our trajectory of our spacecraft, looking at the ascending node and descending node. Which side is the southern hemisphere? Well, if we've defined the arrows as going from this way, and this is ascending node to now descending, that means that this is in the descendant part, and this is the ascending part. So that would mean this is our southern hemisphere. Okay. Now, what I kept putting off before is, what if we just redefined our angular momentum vector in the other direction? Okay, well, I'm going to write this down. It's 2D part 2, electric boogaloo. So we have the same shape, right? I'm going to use the assistance of my iPad on this one. So we have the same shape, same center. Yep. Our periapsis is still defined as the same location. We can have a nice little line there. Okay. So what else? Well, whoa. What else are we looking for? Okay. So if these are flipped, right, up is down. Again, I want to stress that when we have this coordinate frame, right, and our h vector is pointed down like that, all we're doing from this up and down scenario is where we are looking from, right? Like this, when we are looking down at this angular momentum vector, shows that it's down into the page. However, if we flipped our view frame to the other direction, it is now into the page, or up. Or sorry, it's out of the page, which is up. So, what if we did that instead? Okay, so that looks like a couple things. We have our angular momentum vector, and since we are at the bottom looking up at it, it's going to be open. We're just going to go ahead and label this H. Okay, what else? Well, that would mean that the spacecraft looks like it's kind of going in the other direction. So that means it's going like this. All right, so now that we have our, circle drawn, yeah, let's go ahead and draw on our small omega. So notice on this side, right, we've defined it through this way. And that was again looking up at it. However, if we look at it from the bottom side of this orbit, you'll find that it's actually going to look something like this, where it's the negative omega go in the opposite direction. All right, so then we have our ascending node and our descending node. Okay, so we have our ascending node, descending node, and direction. What does that mean? Well, we can still label this the southern hemisphere. Okay, what else can we do? Well, we still have our spacecraft at the same location as the other at 180 degrees around, right? Nothing's changed on that. Okay, well, what if we draw this in 3D? Let's go ahead and get our coordinate system. All right, so a helpful thing that I have always done, right? Not necessarily something you guys need to do. I always find it helpful to draw Earth as a reference. Don't ask me why, it just helps. All right, so I, just like you, can erase part of the coordinate frame that is inside the Earth, and voila. We have our X, Y, and Z coordinate system. All right, so how do we start with the 3D, right? Well, we labeled everything on the 2D plot here. So let's just kind of go down the list again. Well, we can start with our inclination. That's a really easy one, right? We kind of talked about this before, but looking at this, right, you have about 90 degrees to the y-axis or x-axis, right, xy plane, and then you have 30 degrees underneath. So what this kind of looks like at the moment is a little cone, right? Our angular momentum vector can be pointed anywhere along this line of cones here, right? Until we define where our line of nodes is. Why'd you do that? Okay, well, like I said, can't really define this totally yet. We have an idea of where it is, but we don't know where it is. That made sense. So let's look at big omega. Okay, well, big omega is 30 degrees from the x-axis. Okay, cap omega is defined from the x-axis in. Well, 30 degrees, we'll say, is about here. Now I'm going to move that off the earth so you guys don't get confused. That, as a random point in space, is about 30 degrees. My goodness. Okay, good enough. It's about 30 degrees from the x-axis, right? In this direction. And that is labeled that. Okay. And we were able to label that the ascending node. Okay. Well, now that we know where the ascending node is, 180 degrees behind it is where the descending node is. So, a little open spot there, but descending node, that's where that is. Okay. So now that we have the ascending node, the descending node, oh, I just did that backwards. What else can we do? Well, now we can look at the inclination again, right? Inclination is, again, the perpendicular of this, right? That's why it's coming out of the page in this 2D plot and, it's going down into the page on this 2D plot and out of the page on this 2D plot. Okay, well, let's look at this one since we've been referencing this one. The ascending node is here, right? And the descending node is here. This is looking at down. And we can confirm that with our inclination where it's pointing down and it's in this direction. Okay, so that makes sense. So then we can kind of just go ahead and finish that line there. And again, I'll just go over this real quick. We have our ascending node, boom. Descending node, boom. Our H vector is going down into the page. Okay, ascending node, descending node into the page. And we then confirm that that our inclination is over 120 degrees and shows that it's below the XY plane. Okay, well, now that we have that, let's just go ahead and draw our orbit, right? It's perpendicular to the H vector, angular momentum vector. So we're just going to go up and down, and that'll go through descending node, and we're going to go ahead and draw like that. And it'll kind of go through the earth like that. You do not have to, I want to stress that you do not have to sketch through the earth or anything like that. So I'm going to just go ahead and erase this just to make it a little clearer. Helps kind of open up space on your drawing because it's going to be cluttered as it is. Okay, so what are we missing in terms of our orbit, right? Okay, well, we have our periapsis labeled here, but nothing on here yet. Okay, well, let's fix that. Small omega is defined as our ascending node to our periapsis. Well, here's our ascending node. Let's just go ahead and go 30 degrees up. And there's our RP. Boom. That's pretty simple. What else we got? Okay, well, on this diagram here, our spacecraft is 180 degrees away from our periapsis. Well, what does that look like here? 180 degrees is somewhere over there on that side of the orbit. So we're going to just go ahead and label our spacecraft as somewhere down there. Now, I also, again, like to put arrows on my orbits to kind of show the direction, make it a little bit more clear where it's going, what way it's going. So let's kind of go through this again real quick, shall we? We used our eccentricity for the ellipse. Yep. We got our inclination to help us with our angular momentum vector, both in 2D and 3D. We only used our cap omega in our 3D orbit to help us define where our ascending node is. We then used our small omega in both our 2D and 3D plots to define from periapsis to ascending node, or vice versa in this case. And then we used our true anomaly to look at our spacecraft location. All right, and again, this 2D plot is just showing what this is, but our opposite angular momentum vector, looking at it from a different angle. So 2D, we'll call this number 1, right? Viewpoint was up here. We'll call this number 2. Viewpoint was this way, right? And I'm just going to confirm with you and show you that they're the same orbit, and all their features are just, they're just shown differently. So looking at it like this, right? We have the orbit going in this direction. However, if you look at it, right? Here's our periapsis and here's our body, right? So showing that it goes from ascending node to descending node through our periapsis. Okay, well, let's look at this 2D, right? We have our ascending node and our descending node, and it goes through periapsis in this direction, right? Okay, well, what else? Well, in this direction, it looks like ascending node is this way, right? Okay, well, ascending node in RP, here's our small omega. And then the larger part of the orbit is shown in the southern hemisphere. All right, well, we have working backwards from the direction of our ascending node to our descending node. Well, here's the larger part of our orbit, descending node, or ascending node back to the descending node. Okay, let's do a quick speed round, shall we? Here is orbit C from problem 7. Now, I have not done this before, right? This was a random orbit that I selected from your homework that you can easily sketch out. So let's go ahead, right? Ellipse, right? Easily. So let's start with 2D. All right, let's go ahead, speed run this a little bit. We got a ellipse with a circle or a central body over on the left side, as I always have it. I'm going to look at my my inclination. My inclination is less than 90, so I'm going to go ahead and draw this as an open circle. Go ahead and boom. All right, now looking at the rest, right? We don't need cap omega yet. Let's look at small omega, 30 degrees. Well, I'm going to define my periapsis is right there. I'm going to draw a little line going through. And because it's in this direction, right? Because it's open and we are viewing it, I'm going to keep the same convention up here of using the clockwise notation, right? So, what are we going to go ahead and do that? No, I totally lied to you. Yeah, no. I'm going to be drawing it in this direction here. And again, I'm defining that because I like it when H vector is open, it's going to go in this direction. Yep, sorry. Counterclockwise direction, and when it is into the page, down, I have it as the clockwise direction. That is just the notation that I've frequently used. What did I do? Okay, so ascending node, right? Okay, so 30 degrees. So we're just going to go work backwards here at negative omega. Go ahead and draw this ascending node, descending node line. I'm going to go ahead and label my southern hemisphere. Now you'll notice here that I have two locations. This is what is given on your homework as 180, but I thought that was really boring because we just did that. So I am going to go ahead and substitute as 345 degrees as your new true anomaly. All right, so what does that mean? We're going to go 345 degrees around, which is pretty much negative 15 degrees. Did I do that math right? Yes, I did. So negative 15 degrees is like here-ish, which means I can take away that and label my spacecraft. All right. I've got spacecraft done, ascending node, descending node, angular momentum, which I can go ahead and move. My goodness. I've got my periapsis labeled and my direction of my spacecraft and my southern hemisphere. So let's go ahead and do my 3D plot. 3D. Oh gosh, that's blue. So start out with our 3D coordinate system with Earth. Zoop. I always draw my x-axis a little bit smaller accidentally. Here you want to make sure you are labeling all of your axes still, right? Make sure that happens. Don't forget that. Okay. Well, what do we start with? 210 degrees. Now, this is a little weird, right? 210 degrees is this plus over here, which means it's somewhere over there. That is where our ascending node is, right? Okay, well that means that our descending node is over here at 30 degrees, right? 210 minus 30 is 180, so that makes sense. This is our descending node. Okay. Well, let's draw our orbit then. Ascending node to our descending node. Well, let's go ahead and get our angular momentum vector in there then. This is ascending, this is descending, and this is coming out of the page. Inclination is 20. All right, so how do we actually draw that? Okay, well, it looks kind of like this. Draw it up like that. 20 degrees-ish. You know, it ain't perfect. It looks like that. Now, why did I do that, right? We got ascending node to descending node. I'm thinking of how am I looking at this, right? This is coming out of the page. I'm looking top down, right? Top down. We got top down. I'm going to go ahead and connect my ascending node all the way over to my descending node. That was really bad. We're going to try that again. I don't know why my iPad's doing it like this. Ascending node, connect over to my descending node. All right. And the orbit's going to go through there. Now, again, you want to make sure that you can label the rest of your items here, but this is not drawn to scale because obviously this is, you know what? I can do this partial. There we go. There we go. Draw this a little closer. You know why? Because I got my periapsis between my ascending node and my descending node. About 30 degrees again. So it's going to be over just about here. That is my RP. Okay, well, where's my spacecraft? At 345 degrees, right? if our ascending node is on this XY plane and our our periapsis is 30 degrees up, right? That means it's somewhere halfway in between ascending node and our periapsis, which means it's our spacecraft right there. Okay, let's go ahead and just double check here. We've got our ascending node, we've got our descending node, we've got our angular momentum vector, along with our inclination angle labeled, periapsis, spacecraft, and our coordinate system. So I think that's it. I hope this really helps, and yeah, good luck on your exam.